This is Exam 1 from Spring 2019 for Calc 3. Let's get going. Question 1, we have a line that passes through a point and that is perpendicular to that plane here. And we are trying to find the point at which this line intersects the YZ plane. Okay, so we're going to parametrize this line, and this is actually much easier than it might look. It's a little confusing here. Perpendicular to the plane, how do we find that? Well, we know that the plane is defined, or the coefficients of x, y, and z in the plane define that plane's normal vector, and the normal vector is the only vector that is perpendicular to the plane. So this is going to be the slope of our line so that we stay perpendicular to this plane, and we know we have to go through this point. So our line, they want us to call it L, so I guess we'll call it L, equals, for every unit t, we want to move this here, so 1, -2, 2, t, plus, and then our constants here, the point that we want to intersect when t is equal to 0, -1, 1, and 2. So this right here should be our parametrization, where our slope is the same thing as the normal vector of this plane over here, so that we stay perpendicular at all times. And we want the point when this line intersects the YZ plane. Well, we intersect the YZ plane when x is equal to 0. And what we're going to have to do here is figure out what value t needs to be equal to for our x component to be equal to 0. So our x component is formed kind of from this equation. And in fact, I know that a lot of people don't use this form, so we can rewrite this as x equals -1 plus t, y equals 1 minus 2t, and z equals 2 plus 2t. And that's probably an easier way to show it, but it is equivalent here. So x is equal to 0 when t is equal to 1. And when t is equal to 1, this guy right here is going to be -1, so we have 0, -1, and 4. So 0, -1, 4. Answer choice E is our correct choice. Let's see, we're going to find the equation of the plane that passes through this point here and is perpendicular to two other planes. So whenever we need a vector, in this case we need a normal vector that is perpendicular to two other vectors, we can pull these normal vectors out as 2, 1, -2, and 1, 0, 3. Whenever we're looking for something mutually perpendicular to two vectors, we know that that's a case for the cross product. And so if we cross these, 2, 1, -2, 1, 0, 3, we will get 3, -8, and -1. So if this is our normal vector, then all we're going to have to do is set this up as the equation of a plane, 3x minus 8y minus z, and then plug this point in to see what our constant is on the right side of our equation. That's going to be 3 plus 8, so 11 minus 2, so 9. And our answer for number 2 is B. And you can kind of, if you want to see this a little bit more visually, we can draw it out a little bit. So we want the plane that is perpendicular to two other planes. And if we kind of draw these planes normal vectors in here, we see that the cross product is going to give us either one of these two mutually perpendicular vectors here. And so our plane is, oh no, this is going to be bad, but I hope you can kind of see how, this plane's not looking good, but hopefully that gives you a little bit of a sense, if this is our normal vector, how that plane will look in relation to the first two that we are crossing to find it with. Let's find a vector function that represents the curve of intersection of that cylinder and this plane. This is the reason, this question is the reason that I put this exam off. This is one of the last ones that I've done, just because up until this morning, I really didn't have a good explanation for, why this one worked the way it did. So, but now I do. So let's see how it goes. We are looking at the intersection of a cylinder and a plane. So always in this case, what we're going to end up with, let's kind of draw this out. We have some plane with some arbitrary slope in 3 dimensions, and then we have our cylinder coming up through it. And so really, we're looking at this curve here, which is kind of like a cookie dough cutout of the cylinder that has, this is bad, that has passed through it. And so this cylinder, this cutout that we've made is going to have the same slope as the plane, but it's going to be, circular in shape if you look straight down on it. So to parametrize this, what we're going to start off with is just by setting, let's see, y equal to cosine t, z equal to sine t, and that's just because we need to be able to trace a full circle. Like we said, if we look straight down on our little cutout of the plane, we're going to need to be able to trace a whole circle. And since this cylinder is on the YZ axis, this parametrization will get the job done. Okay, so now finally, and this is actually a very, very quick question, all we're going to have to do is plug these 2 parametrizations into this guy and put it in the form x equals. So we have x plus sine t plus, x plus cosine t plus 2 sine t is equal to 3, or x equals 3 minus cosine t minus 2 sine t. And our answer is B. And so I hope you can kind of see how we need this kind of base parametrization in here to fulfill the requirement that we trace a circle with respect to the y and z axes, but we also have to account for the weird slope that this plane gives us when we take x into account. And so all we're really doing is taking this little parametrization and plugging it into our equation for the plane. So 3 is B. Question 4, let's find a curvature. So the formula I always use for this, I don't deal with any kind of, unit tangent vectors. I'm not even sure what those equations are anymore. All I do is magnitude V cross A over magnitude V cubed. And this one, so far, has not let me down. So let's find V and A before we can do anything. So we know that V of t is just the derivative of each component of r of t with respect to t. That will give us 1 t squared, and then A of t will be 0, 1, 2t. And at this point, we can completely get out of the land of t's. We don't need to be dealing with variables anymore because we are looking for curvature at 1. If they were just looking for curvature at any arbitrary t value, then we would need to leave it in terms of t, but we can find v of 1 and a of 1 at this step, and we'll be fine. So 1, 1, 1, and 0, 1, 2 is our velocity and acceleration at that point. So our first step, well, what I'm choosing to do first, we're going to find our numerator. That's just going to be a cross product. I'm taking a magnitude, so our cross product will be 1, -2, 1. And the magnitude of this, well, we're going to get 4, 5, 6. So the magnitude of this vector right here is root 6. So we have root 6 on top. And then on the bottom, we're looking for the magnitude of v cubed. Well, the magnitude of v, if v is just 1, 1, 1, is going to be root 3. So we have root 3 cubed up there. So obviously, some simplification is going to have to happen here. In fact, one of these is equivalent to this guy, but we do need to figure out what that is. So first off, let's take this square root and put it around everything over here. That makes things a little bit more clear, because now we can replace this down here with a 27. 6 over 27 is the same thing as 2 over 9, right? Yes, okay, good. And this will just simplify to root 2 over 3. And there's our answer for C. Question 5, a particle travels with position vector r of t given there for t greater than or equal to 0. Find alpha greater than or equal to 0 such that during the interval of time from 0 to alpha, the particle has traveled a distance 20. So introducing this whole alpha thing is really unnecessary variable-wise. Really, all they're asking for, find the value t such that the particle will have traveled a distance of 20. And we know in the end that the integral we're going to be taking, and I'll use alpha, why not, is going to be an integral from 0 to alpha of the magnitude of r prime of t dt. And we need this to equal 20. So let's find these things. R prime of t will be 3, 4 cosine t, negative 4 sine t. The magnitude of this will be the square root of 9 plus, well, 16 cosine squared t plus 16 sine squared t, so plus 16. We can simplify that right off the bat, and all of this will be root 25, or just 5. And so we can replace our magnitude, r prime of t, with a 5 in here. This integral will just give us 5t evaluated on 0 to alpha. This 0 component will give us 0. And alpha up here will give us 5 alpha. So we see that 5 alpha minus 0 has to be equal to 20. 5 alpha is 20, so alpha is 4. 5 is D. Question 6, a particle has acceleration given there. It is known that the velocity, we're given an initial velocity and an initial position, all for time equals 1, and we're trying to find the magnitude of the position vector at t equals 2. Again, very, very standard kind of question for them to ask. All we have to do is integrate our components of A and match them up with our initial velocities and positions. So the integral of A of t dt for all these components will give us 3t squared minus 2t. And then we see that when velocity is equal to 1, we want this component to be equal to 1. If we plug 1 in over here, we're already meeting that condition, so we don't need to add any constants. For our next component, we integrate and we will get 1 over t. That's a bad t. There we go. 1 over t, and when t is equal to 1, we want this component to be equal to 1. That's already satisfied. And then finally, integrating the z component, so integrating 0, we get 0, and we'll need to add a constant of 1 to match up with v1. So this whole thing is our v of t. Now our integral of v of t dt will give us t cubed minus t squared, and we see that r1 for this component should be equal to 0, so we've already met that condition. over here we get ln t, and when we plug 1 in here, ln of 1 is in fact 0, so we're good there as well. And then t, we're going to have to add 2 in order to meet our final condition over there, and this is r of t. And so finally, they want the magnitude of the position vector at t equals 2. If we plug in 2, r of 2 is going to be 8 minus 4, so 4 ln 2 and 4. So we are left with 32 plus ln 2 squared, which is answer choice C for question 6. The level curves of this guy are what? So remember, whenever we're doing level curve questions, we're just going to set f of xy, which you can also think of as z. It's just the output of whatever we put in for x and y. We can set that equal to some constant k, and then solve our equation and try to put it into some form that we'll recognize. So root x squared plus 1 minus 2y. Let's add 2y over and square everything. So 2y plus k squared equals x squared plus 1, or 2y plus k squared minus x squared equals 1. And this isn't really, a form of an equation that like pops out to you right off the bat, but in fact, this is just a hyperbola that's been shifted along the y-axis by some amount k. So in fact, this coefficient doesn't matter, and this value k doesn't matter, and we can have the same type of curve there if we get rid of all of that, and that's just your canonical definition for the equation of a hyperbola. So there we go. Question 8 is a real pain. I'm not looking forward to doing this one. We are trying to find fxyz at 1, 2, 3. Okay, let's go. So fx, the partial derivative of this guy with respect to x, we're just going to hold y and z as constants. And this is the only easy one. We're going to get z over root y squared minus z. fxy is going to be, let's see, z times 2y over y squared minus z to the 3 halves times negative 2/3. No, sorry, not times negative 2/3, times negative 1 over 2. So we're just going to be left with that. I'm mostly sure that's correct. Oh God, I hope I don't get this wrong. And then finally, fx yz is just the derivative of this. With respect to z, we're going to have to use the quotient rule. That's going to give us, let's see, negative y squared minus z to the 3 halves plus yz multiplied by negative 1 y squared minus z to the 1 half times 3 over 2. All of that divided by y squared minus z to the 3rd. So the chances, if you're hearing me talk right now, I just did all my my differentiation correctly. I think that's very unlikely. But the fact that whoops, the fact that you're hearing me, that's a good sign. It means we did things right. Okay, so f, x, y, z evaluated at 1, 2, 3 is going to be -2, and it would be a good thing to figure out what this little guy is going to be because we have to do it, 3 different times. Y squared is going to be 4 minus 3, so that's just 1. So -2 times 1 plus yz, so 6 times -1 is -6 times square root of 1 times 3 over 2. So our whole numerator should be -11. -11. All divided by 1. Okay, is our answer B? 8? Oh my God, 8 is B. Okay, I'm sorry I couldn't, lead you through that differentiation a little better. That's not what I'm here for. There are online calculators that will, give you paragraphs and paragraphs about it. I'm sorry. This is just a truly painful question to do. And this is by far the worst partial differentiation question we've had in a very, very long time. Question 9. We have a multivariable chain rule question where E is composed of R and theta, R is composed of S and T, and theta is composed of S and T, and we're looking for partial Z, partial S, or I'll just write it as ZS. So by the formula for the multivariable chain rule, ZS is going to be ZR RS plus Z theta theta S. And all we have to do is fill in these 4 blanks here. So ZR is the partial derivative of Z with respect to R, which will just be e to the R cosine theta. Z theta, on the other hand, is going to be negative e to the R sine theta. RS will be 12t, and theta S will be S over root S squared plus T squared. So let's shove all these guys together and see if we got a correct answer. So ZR times RS will give us 12t e to the R cosine theta. And then the other two multiplied together and added to this one will give us negative e to the R sine theta times S over root S squared plus T squared. Okay, and it looks like they've factored in e to the R out of everything, so that will give us e to the R 12t cosine theta for our first section. That lets us take out B, D, and E. And then finally, minus S sine theta over root S squared plus T squared. And that leaves us with answer choice A for question 9. Question 10, the direction in which f of x, y increases most rapidly at 1, 0 is what? Okay, so we know that if we're looking for the direction of greatest ascent or greatest increase, which is what they're talking about here with the increases most rapidly bit, we need the gradient vector. And our gradient vector in this case is just going to be fx, fy. And in the end we're looking for this in terms of a unit vector. So fx will give us 2xy plus y e to the xy sine y, whereas fy will give us x squared plus x e to the xy sine y plus e to the xy cosine y. Isn't this just fun? This exam has much more tedious math than the vast majority of the past ones do, but maybe that's the direction they're trying to go in with these exams anyway. Okay, we're plugging 1, 0 in here, and so fx, we have a y as a, leading coefficient on all of these, so this whole thing is going to be 0. Whereas looking over here, well, this x squared is going to give us 1. This guy right here, well, the sine of 0 is 0, so this whole thing is going to be 0. And right here, e to the 0 will give us 1, cosine of 0 will give us 1, so this whole bit is 1. And so as a result, fy is 2. So this gradient vector that we're left with is 0, 2, and they could have been very sneaky and put that in as an answer choice, but they want things in terms of a unit vector. And the unit vector of 0, 2, drum roll please, is 0, 1. And expressing this in the ijk terms that they want, that's just j. So 10 is B. There we go. We're looking for a tangent plane. We know that the tangent plane equation in the end is going to be z minus z naught equals zx, x minus x naught, plus zy, y minus y naught right there. We know that all of these naughts are just going to be from the point that we're evaluating our tangent plane at, so we can go and replace those right off the bat. Plus 6 minus 2 minus 4 in there. And then these zx's and zy's are just the partial derivatives of f of xy with respect to either x or y. We'll get 1 and negative y. Evaluating these at 2, 4, negative 6, we get 1 and negative 4. So we can replace this up here and this guy. There we go. Just did a little bit of simplification there. And now it looks like all of our answer choices have all of our xyz variables on one side. So z minus x plus 4y is going to be equal to 8. And our answer choice is right there, answer choice D. But it's also important to remember that with this question that we can only use this equation that we had up here, the z naught equals zx, x minus x naught plus zy, y minus y naught, if our equation is explicitly defined in terms of z equals something. Otherwise, our equation is slightly different, and you'll definitely run into those questions if you have not already. Okay, question 12, we want a local minimum. Whenever we see the local when these min-max problems come up, that means we're using the second derivative test. We're going to be using the matrix fxx, fxy, fyx, fyy. If the discriminant of this matrix, aka A times D minus B times C, if that value is greater than 0, and if fxx is greater than 0, we have a local min. If fxx is less than 0, we have a max. If the discriminant is less than 0, we have a saddle point. And if the discriminant is equal to 0, we have no clue at all. Okay, I'm going to make these rules really tiny and put them up here. And also I'm going to, put the matrix over here too, because we're going to need some space to find these guys. Fx and Fy are our first. To compute, we're going to get 12x and 6y over here. And we know that the only possible points that we can use to evaluate our matrix are the critical points, and critical points can only occur when both fx and fy are equal to 0. And we can see in this case, this is only true when x equals 0 and y equals 0. So this is our critical point. This is just about the easiest second derivative test question you could possibly have. And I haven't messed anything up here, have I? Yeah, no, I haven't. This question just really is that easy. Our answer is 0, 0, because that's the only critical point that we found. And we'll see that if we set up our matrix, we will find fxx as 12, fyx and fxy as 0, and fyy as 6. So this discriminant is positive. We satisfy that condition, and fxx is greater than 0. So we have a local minimum at 0, 0. The answer to 12 is C. So kind of the story of this test is a bunch of really yucky math that they make you do, and then they give you a very easy min-max problem at the end, where min-max problems can really get out of control sometimes, especially if you get one of the horrible ones where you have to, where you're usually given an ellipse, and you have to search the outside of the ellipse for absolute max and mins, and also the inside of the ellipse for local max mins. And so you have to apply kind of two sets of tests, and that's really no fun. This test, on the whole, one of the harder ones, but I mean, you'll look back on this when you're studying for the final and wish that your material was like this. Okay, see ya.